concurrent objects. Actually, these slides were taken from the author's companion site for the multiprocessor program. Okay, what is it? Okay, as we said, in this part of the course, we are very much interested in dealing with the system software aspects of concurrency. So basically, what happens inside your computer to support parallel execution. This is in focus here. Right. So a fundamental concept here is how to deal with concurrency at the level of objects. Right. Usually, people like to program object-oriented languages. They're much easier to program, and from the point of view of software engineering, they have nice features and so on. Right, so what happens is that this is the computation model you have. You have a memory, and then you have objects inside the memory. And these objects, they are maybe communicating or associated with other objects. And what happens is that you have many processing units, and every processing unit can be operating concurrently on maybe the same object or different objects. Sorry, I wasn't very clear here. Maybe the object here is the not line. These are the methods inside the object. Right, so as you can see, maybe these two processors are running on the same objects, different methods, or maybe the same method again. And there's some overlap here. Maybe there's some sharing between the objects. Okay, so the question is, if you have many things running at the same time, obviously things becoming more complicated. And of course, usually what you do is you lock. You make locks. Whenever there's something shared, you just lock it and work on it. But usually if you do that, you lose performance. So what's interesting here is to see how can we very much not use locks, right, and still have good correct performance, correct execution. Right. So anyway, so these are the general objectives of these slides. Basically, what is a concurrent object? So we want to start from the beginning. So what's an object? Right. Object is just an abstraction from the software point of view. Right. And usually, just some simple description. So usually, object you have some data and you have some functions. Usually, the functions are called methods. So these two are like one unit. And what's interesting is that in the object, you invoke a method. So basically, if you have an array, okay, you say insert element, or a queue, for instance, you enqueue element or dequeue element, and so on. You operate on the data. So that's why it's object-oriented. Right. So if you want to talk about concurrent object, right, the concurrency here means that you can have many threads or processors invoke maybe the same methods, or running the same object using the methods of this object, maybe the same method, maybe different methods, but they're still operating on the same data or on the same object. So things can go crazy if we are not careful. Right. So how to describe one? Easy. How to implement one? It's easy to show, but then how to tell if we are right? This is difficult. This is very important. Reasonable. Okay. So let's see how to describe one. Maybe we'll go through the animation here. They have a nice things. Right. So what you see here, this is a queue, a FIFO queue, first in, first out, just a standard queue. And this queue is the object, and you have two fundamental operations, enqueue and dequeue. This slide you can see the enqueue operation. So So Q is the name of the object, right? Q, and then this is the notation you use, dot, and then you write the name of the method you want to invoke, like in Java or in C. And this is your parameter. So basically, your parameter here is another object, and you want to enqueue this green object into the queue. Right. So basically, your queue now has got two elements. So when you make this operation, you basically want to insert this green object into here, in this empty place in the queue. Yeah. And then you have the dequeue operation, which is the opposite. What you do is you take, you remove one object, but this time from the head of the queue, right? Because it's FIFO, first in, first out. So the same, maybe another processor or thread will issue queue.dequeue. So queue is the object, .dequeue, so it will remove one object from the queue. And this is usually from the head. So basically, this is a typical example of concurrent objects. So now let's see what's going to happen if we have these two threads concurrently enqueuing and dequeuing the queue. The standard implementation usually is based on locks. Right? So what you do, you have a lock. And yeah, so basically this is a lock-based queue of type T, generic type T. It's got this is what you need to know about the queue. You need to know the head and tail and array of items. This is classical implementation using circular array. And then you have your lock. Right. So your lock, this is basically a shared object here, and basically this allows you to lock and unlock the lock so that you can guarantee that only one can do some important operation at a time. Right, anyway, so this is some initialization here, and yeah, this is the protection of the whole system. The whole structure is protected by a single shared lock. The initialization, I usually head equals 0 and t equals 0, so head equal t. Now, have a look here. So actually, what you see here, this is maybe a nice representation. Yes. Basically, it's a circular array. Right? So it is array, but you implement it in a way to be circular, basically by using modulo arithmetic and so on. So this is item 0, 1, 2, 3, and so on till the end, and then you start again from 0. So basically, if you enqueue two objects y and z, this is what it would look like. The head will always point to the first element, which is 0. And tail will point to the empty place after the last element of the queue.
So for the last slide, when the end equals the tail,
so it's empty.
And maybe it's full.
Well, there's overflow, of course, but you have to check. So you don't insert an element if it's full. Yes. Yeah. So maybe you just sacrifice with some location or something. So your queue is like maximum capacity minus 1. And then you have a lock here. So this is your lock. Basically, if you want to do some operation on the whole structure, you lock, and then you operate, and then you unlock. This is a classical way to do it. So as you can see, this is the dequeue. It will lock first the lock, and it will wait here until the lock is succeeded, and then it will go there. So if it's empty, it will say it's empty. If not, you take one item. So basically, you take from the head. And as you can see here, head is always incrementing, so you always take the modulo. So yeah, it takes an element, increments the head to point to the next element, return the x, and then makes a lock. So maybe it's typical. This is mutual exclusion. I think we described that. Okay. So, all right, this should work. But of course, the problem here is that you actually don't allow for concurrency. So basically, you transform this kind of concurrent object into a sequential object. Right? Nothing can happen in parallel. So it's easy to reason about, of course, and it's correct. But maybe from the point of view of performance, it's not good enough. So let's assume that, okay, now we have another implementation without mutual exclusion. So basically anyone can do anything. So there's no locks at all. And to make things simple, we assume we only have two threads. One that always perform the enqueue operation and the other the dequeue. It's like producer-consumer sort of relation. Right, so this is how it looks like. This is your queue, with head and tail items, there's no locks. Yeah. And then enqueue would basically wait until head minus tail equal capacity. Okay, this is another way to do it, like the maximum capacity of the queue. So you wait until when it's full, you wait, you busy wait, and then when it's not full, you get out there and you insert your new element. And then in the dequeue part, you do the opposite. You wait when it's empty, and when it's not empty, you go there and remove one element from the head. And head plus plus. And then return that. Okay. So as you can see here, okay. Of course, there is some waiting here if you're empty or full, but if the queue is not empty and not full, just typical, then you have an enqueuer that is concurrently adding something while the dequeuer concurrently removing something. Whether this is correct or not, this is what we're going to reason about. But this is, what we mean here by wait-free implementation. Right. So there is no like waiting to acquire the lock, right, or waiting for the other guy to finish. You just go ahead and work. But of course, here, if you are not careful, you can end up having wrong results. One interesting thing maybe we can try before getting into more slides is that what will happen if you just change the order of these two lines. Let me just put it in here. Will it work? Why?
First, MCQ is empty, and enqueue method try to put something in this queue.
Yeah.
And we change the order of tail plus plus.
Mm-hmm.
So dequeue and the other thread try to dequeue something.
Mm-hmm.
If we change the tail plus plus, queue will look like as it contains something in it.
Mm-hmm.
So the queue will try to take an initialized object.
Yeah, that's correct. So basically, if you do this change, basically what you're waiting for here is the tail. Yeah. So if you want to dequeue something and the queue is empty, you wait. Right. So let's assume the queue is empty and you enqueue something here. So you incremented the tail, but you haven't yet put the new object. So the one who is doing the dequeue process would now say, oh, there's now some object, so it will take it, but it's not yet written. Yeah. So just a very simple change like that can be wrong, and not always wrong, because it can be correct. If the other one is delayed a little bit, so maybe before just reading, this one is fast, and so sometimes it can work, sometimes it doesn't work. Okay, right. So there's some description about it. So queue is updated without a lock, and the question is, how can we define what is correct? Right. Okay, what we did here is we defined it in a term, or how do you call it? We can say it's kind of intuitive. Let's say like, this is the way it works. But usually, if we want to be more precise, we need to think about how to describe correctness, or how to show that this operation is correct. Right. So usually, in order to do that, you need to make some specification. To say, right, this is how it works. And usually, the specification you do is a sequential specification, which means that you say enqueue itself would enqueue an element into the queue. Right. The queue itself will remove an element from a queue. Right. You don't do specification like okay, I am now executing 2 statements from enqueue and then 1 from DQ. It's very complicated. But what you want usually in description, you just assume as if there's only someone who's doing this sequential task and another one is doing another sequential task. So usually the specification is sequential because it's much easier. Right, so this is what you have. Alright. So concurrent we need to specify both the safety and the liveness properties of an object. Right. Right. So by safety we mean that it's okay. It's safe. It's correct. You get a correct result in the end. Aliveness means that okay, they are alive. Okay, you're not like deadlocked. You're stuck. You're doing nothing. So you want to make sure there is some execution happening, and whatever happening is correct. Right. So okay, let's see how to show that. Right. Basically, it's usually easy to, as I said, to specify the correct behavior of an object using sequential specification. So what you do, you assume that your object are accessed sequentially, never concurrently, and every object has got some state, data, or values of the data, and this is usually defined by its fields. So for instance, in the queue, the state would be the number of items and the objects that are inside the queue. And then every object, aside from the data or the state, you have methods. And this method will change the state. So we have, for the example of the queue, you have enqueue and dequeue operation. Right. Usually people who do formal specification like very much to specify preconditions and post-conditions, which is like what would be true before invoking a certain method and what would be true after invoking a certain method. Right. So you specify like, okay, for instance, for the queue, okay, the queue is empty, and then you make an enqueue operation. So the post condition would be there should be one item in the queue, and so on. Yeah. So usually I remember when I was in England, they used something called Z language to do that. It's very much like mathematical language. And people who are very much interested in software engineering usually do these things. So for instance, this is the example for the dequeue operation. So for the dequeue to work, the queue has to be non-empty. The post condition, the operation itself would remove one item, which is the first item of the queue, and the queue itself would be free or would contain one less item. So one item is removed from the queue and one item is returned by the function. It's the same item, but here is just some more detailed specification, which is that this object is returned to the caller and it is removed from the queue. This is what it's said.
It's the same thing.
No, this returns, which is like, okay, something happened in your function, you return something. And the condition is that what you return is the first item in the queue. And the other thing, the state of the queue itself has changed. Now you have, instead of 3 items, you have 2 items. Okay. Usually, actually, maybe this is English, but usually people like to use, as I said, mathematics. So, right, queue is not empty, whatever. It's not phi and whatever. So usually people like mathematics to specify. It's more precise. Anyway, yeah, okay, another specification for the queue operation, that the queue is empty, and therefore you have an empty exception, which is thrown, and the queue state is the same. So basically this is like the formal specification. So usually, here's some justification why should we go for the serial or sequential. Yeah, usually it's easy, documentation is nice, and it's very easy to add new functions and so on. But if you imagine that we provide some concurrent specification, like for instance, for our method of enqueue and dequeue, if we change this line of code, then you have to describe what will happen if this one is faster, and so on. So you try to find all possible combinations and try to find out what will be the output. So usually this will be like exponential. It's crazy, of course, to do that. Right. Okay. Now, if we want to talk about concurrency, now, okay, maybe in the specification itself, this is difficult, but now, if you want to analyze concurrency, right, how will we do that? Right, let's try to think about what will happen when you run a function or a method, or many methods actually concurrently. Right. Usually, a very important aspect we have is time. Right. So let's assume we have this queue with two objects here. And then at 12 o'clock, this blue processor or thread, he wants to insert a new element, green element here into the queue. So what will happen usually is it will start working. So at 12 o'clock it will start working, and then processes until some time later. So actually what will happen is that your invocation or your method does not happen immediately. Actually there is some kind of time interval where you do the work and you finish. Right? And this is one important concept. It's very simple it seems, but it is very important. So you do the work and then right, as you can see, the element is not inserted yet. After a while it is there, and then after a while, maybe at 10:01, another one here want to do something. Yeah, sorry, it's the same. Yeah, you're right. Yeah, okay. So it's the same processor, yes. The return here is void because it's in queue operation. So that's fine. So anyway, so what happens here is that at 12:00 you do your enqueue, at 12:01 you finish. You got it. Okay, null response, but you finish. So you take maybe 1 minute in this example to do the work. Right, so if you have this sequential specification, usually you have time, but you don't know how much time it will be, but there is some time. Right. And for concurrency, you find out that the call itself, it's not like one thing or event that happened at a time, but usually it's some interval of time. Maybe in sequential specification, the time here is not as important because it's just like it will happen. But here it's big story because if it takes a lot of time, maybe something else will overlap and so on. So overlapping here is very important. So let's see here an example of overlapping. So now you have this blue processor doing something, PQ or DQ, whatever. And while this one is still working, you have another processor, the green one, he wants to do another call to the same queue. And to have even more interesting scenario, okay, you have another processor working there. So as you can see, there is no, in this example, there is no like free time or idle time. Always something is happening. Right. So all methods are running, as you see, in overlapping way. So now things become more complicated because in the sequential specification, what you do is you say, I don't know what's going to happen when you call, but when you finish, this is the response you get, like the post condition, where you move the element, the state of the queues, blah, 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 and so on. But here, if you want to understand what's happening, as you can see, things become complex. Right, so this one calls. Right. Of course, if you use sequential consistency, or not sequential, I mean locks, right? So you basically transform your problem into a sequential problem. And then, even these methods are overlapping, they would execute sequentially. Like if this one goes first, it will acquire the lock. This one will have to wait, and the other one will have to wait. When this one finishes, the second one proceeds. So you transform them from this kind of overlapping time into sequential. Of course, but much easier to reason about. But here, maybe it's, as you can see, faster. But now the question is, how can you tell this is correct? This is a very important question. And not only how can you tell, how can you guarantee? Right. Right, so, okay, so we talked about sequential, and sequential is nice and easy, blah, blah, blah. Right. So for the concurrent execution, to reason about the correctness, you need to make sure that all possible overlaps, they still provide something meaningful and correct. But yeah, usually this is a very complicated task. And actually, if you're interested in analyzing this kind of like general systems, actually I would very much encourage you to look at Hydla, I think, or Hydla, I can't remember exactly the name. This is a system developed by Professor Owaito at the University of Waseda. Basically, he's doing model checking. So he developed his own language that can describe this kind of concurrency. And you can run, and it generates very nice graphs of states of all possible combinations. And then you can see what's happening and check if it's correct or not. But I think you can tell, like, we have very simple examples, and yet you have very big state space. But this is very interesting if someone wants to have a look. You can download the tool from Professor Ueda website. And actually, he got some handouts, maybe we can find them. He gave us some very nice talk about it. And yeah, so it would be nice if someone wants to try to use it. Anyway. Right. So the question, as we said, how can we tell that we are correct? Right. So this is what we did intuitively when we talked about this example of EQ. In EQ, we reasoned that if you have locks, this is easy. And even if you don't have locks, which maybe shown you that very quickly, we've seen that this tail plus plus, it looks, okay somehow. But let's, look more carefully. So this is what I said. If you have two concurrent methods like that, so when you insert locks, things look like that. So basically, you have here two operations, DQ and InQ, and everyone will try to access the lock first. So you have two threads here. So the green one is more luckier. So the invoke succeeds. The lock, invoke succeeds, and therefore he obtains the lock and executes the EQ operation. The other thread is unfortunate, he has to wait, so the lock here does not succeed and it blocks. Until this one finishes and executing the unlock. Right. So then it enters. So as you can see, the EQ happens and then the DQ sequentially. All overlapping here is just for acquiring and releasing the locks, and it is guaranteed to be mutually exclusive. So there is never these two will be overlapped. This is like the classical way people are doing. So this is EQ and DQ. And as you can see, they map here to the time as separated, not overlapped. So the behavior itself is very much sequential, which is nice. Okay, so usually sequential nature is nice. Now, the authors of the book actually invent a new method, which is called linearizability. And basically, linearizability is that if it is possible, this is what's linearizable. Okay, linearizable means that it is possible to have some kind of linear sequence or sequential sequence of things. And linearizable means that you can impose that, right? So it can be transformed into a sequential fashion. All right. So okay. So in their theory here, in their method, they assume that it is possible for every method you have to define just one point of time inside the interval of each method, so that the effect of the function would appear immediately. Right. So for instance, when we looked at the InQ and DQ, actually the tail plus plus and head plus plus, this is the linearization point. Right. So you can say this point, when this line is executed, all the effect of the method is immediately visible to the others. And before executing this one, nothing is visible. Right. This is not always true. Not always you can find this point. But if you can always find a point inside each method so that the effect would be instantaneously happening in there, then this is linearizable. And actually, maybe we can revise or revisit when we talked about sequential consistency, because usually here things are funnier. Remember when we talked about sequential consistency, and we said that sequential consistency is very strong, and usually in hardware, people don't like to support it because it's not their thing. But actually, the linearizability is stronger. So if you maybe look at this simple example, maybe I've shown you before, but it's worth to see it again. If you have here two threads, and both are doing some EQ operation. So, okay, so you do something like, I don't know, Q dot EQX. Right. And then here, you're doing something like Q dot EQY. Right. So here, when you do, let's say, DQ operation, so what would be the result you get? Okay, you put X into the Q, and then you put Y into the Q. And then you should make it a Q. So yeah, intuitively you should get X. Right? But actually you can get Y. Right. Okay. How? Because sequential consistency said there should be a global single order, right? Visible to all processes, so that it would obey the sequential nature or sequential steps of each thread, right? And would the result can be explained. So again, sorry. If you can explain why Y has happened using some sequential order among all these threads, then this should be correct. So let's see. Can we find some sequential order? Right. Yes. You can say like this one happened first, and this one happened next, and this one happened third. So this is correct because this has to happen before that structure order. Yes, correct. And this one is okay, it can happen anytime. So sequential consistency, you said, yes, this is true, you can get Y. But intuitively, you say, come on, how come? How come we did this in the past and now you're telling me it's here? So the notion of time here is not there in sequential consistency. So here, in the linearization, actually, this won't be possible. Because if you say, like, this is the interval of the invocation of this method, and this is the interval, and this is the interval, linearization has to happen here, at any point here of time. So even if you put it there, so X has to happen at this point of time. So there is no point that this one would read Y, because this has to happen first. So linearization is much, much stronger. Okay, right. Let's. Sorry. Okay, go on.
In our case, if we apply the linearization and thread one do Q dot DQ something, and at the same time thread two try to include something in the queue.
Yeah.
We will provide a linearization at some point in our method. Say, for example, A++ or A++. Okay?
Yeah, no, I mean, you follow the point. T1, where T1 would be?
T1 and T1 and T2 will try to do something at the same time.
Okay.
But according to linearization, T++ and T minus minus and T++ will be linearizable. So thread 2 will
maybe you can draw an example. Just draw one. Okay. Yeah, change it. It doesn't matter. You can erase and try. In Q. Yeah, okay, go ahead.
Initially queue with
Have
one
okay.
item. At this point, T1 will succeed to get but still story correct. Sorry.
Okay. Okay. So I mean, the whole idea is that you, it's not always possible. Okay, like the example we have seen, this is not realizable. Okay, and so if you can find not only one time but always, whatever the execution, you can always find the realization point, then this is a realizable option. Let's have a break here for 2 minutes just to transfer the video file.